If you attended Olivier's lecture, you saw this slide, which was an attempt at showing what versioning is. So you know that books, when they are written, oftentimes they are called final, but at some point you want to add some more information or correct things, and then you get to another version which you publish, and you get a second version of the book, and then a third version. And it's the same with the documents that you write. The first draft of anything is shit, as we say, so you need to rewrite it. Some portions of any text that you write. So in the end, you end up with multiple versions of the same document. Code versioning is about tools to manage different versions of code. And here we are talking about the same ideas, but for different versions of data. So you use the defaults instead, rather than having a text document and having little icons of a spreadsheet. But the ideas are the same. So basically, what I just said is that data versioning is the transposition of the ideas related to code versioning to data files. So more specifically, it's creating at some point in time a unique reference for collection of data and associating a comment or an annotation. This definition is quite general and qualifies a large range of approaches as being data versioning. So it includes also having multiple copies of the file with different names and so on. But basically, why we want to version data, there are three main ideas. The first one is to track provenance and sometimes aid compliance and auditing. Sometimes for some project, you will be subject to auditing, and the auditor will ask you, okay, where does this data come from? Where did you acquire it? What was the evolution of the data through the time of the project? And also to revert errors to a known working state. Sometimes you have data, you work with it, and then you realize, okay, this is some weird inaccuracy, I will correct it. And then all of a sudden, everything falls apart in your chain of work, and you would like to revert to the previous version of the data. If you version the data, that's possible. If you did not, then you need to reverse engineer what you do to just go back to the working state. Also, ensuring reproducibility is important. When you have data, you want to share data. As data evolves over time, it's important to mark data as having some properties at some point in time so that you are able to talk with others about version X, Y, Z of the data and not about the data in general, because you might end up talking about different things if you do not specify exactly the state of the data when you share the data. Also, you can run multiple times the same experiment on multiple versions of the data to see some effect at some point. Also, the tools that are useful for versioning will ease collaboration of the data and collaboration in general by giving you the tools to share the data and copy the data from computer to computer, and also to communicate. This is very important, to communicate the changes in the data when there is some data point removed because you think it might be an outlier or an error in measurement. It's important to associate with that change a text to explain why you think that correction had to be made. So if we are all okay with the why, we should ask ourselves the how, and if it were code, then there would be no question at all. It would be Git. This is the standard for code. And so the whole presentation here will be about why not using Git for data version. The thing is that Git was, and the whole ecosystem around Git, as I said, was designed for source code. And source code is what? It's text file, which is typically small compared to data, and line oriented. And the problem is that data, by contrast, can be large. I'm sure some of you work with terabytes of data files on a daily basis. It can go column oriented changes. Data is not necessarily stored in a text file, as we've seen this morning, and even not necessarily stored in the file at all. So these reasons make Git not the best option, and actually there is no single best option for data version. We can think about the naive approach. This is the very first slide. When you have a change, you copy everything into another directory, another file. You change the name of the file in a clever or not so clever way, and then you call it version. That's the naive approach. There are other approaches, like those three, which I will briefly mention because they might apply to your case, but they are not universal. And then I will talk about using version control with arbitrary types. So how we can abuse Git to work with the files which are not source code. At the end, I will end up with a short tutorial on the tool for Datalad, which is built upon Git to provide a nice user experience for the user who wants to use it for managing data. So first, copy and write approach. This is an idea taken from the database community, where they call it the type 2 slow changing dimension. And the idea is that when you have data, and you know the data will evolve over time, but time is not the primary index of the data, it's not time series. But you know that at some point it will be corrected. What you can do is prepare additional values in the data frame or in the matrix with columns allowing to timestamp changes. So here you see a valid to, valid from, and valid to and comment columns, which are not part of the data per se. Here the example is column student IDs and a note out of 20 for some exam. And you see here, for instance, there's a slight inaccuracy. You know that -5 out of 20 is not a sensible value. And you see that here, rather than erasing this line and overwriting it or changing directly, you can leave it alone, but mark it as obsolete, and then have another line here, which is the same student ID, with the correct value, the start at which this value is valid, and then a comment explaining why we actually have two entries for the same student ID. You see another example here where a 9 was replaced with a 10 by some decision. You see the ID. So this is a way to record the evolution of the data over time and to mark each change with a comment explaining why this change was done. Of course, this assumes that you have access to the structure of the data and that you are allowed or permitted to modify the structure of the data and to add columns like this. So it might or might not apply to your case. Another approach is to use a file library that incorporates versioning in it. This morning, I was talking a bit about HDF5 as a very good file format for storing data, scientific data. There are libraries that write version HDF5. So the idea that within the HDF file, this file, you can have multiple versions of the data, and the management of the versions is done by the library. So rather than using your regular NetCDF or HDF5 library, you can use this library in the same way as you would use in your Python code or Fortran code, except that I'm not sure you can read it here, but this line here says that I'm about to write version 2 of the dataset. So if you are used to using HDF5 files, you can have a look at this library, and it will give you for free the opportunity to work with version data file. And so if you are working on the file and you want to record what changes and how they will change, this is another way to do it, right? Yes.
NetCDF is based on HDF5, so I guess we can do the version system in NetCDF5 directly, or?
I don't think so. I don't know. The thing is that the library will decide the organization of the HDF5 for you at some point. So the way versions are recorded or organized in the file is not something that you have to hand on. So if you have NetCDF on top of it, if NetCDF is not aware that this is a version file, you might need to do to take additional steps in the browsing of the file to find the information that you want, compared to a version that we don't use versioning. But what it creates is a perfectly valid HDF file. So if you open it with your usual way and you see version 1, version 2, you know that you can browse down the branch to see the files that you are looking for, the data that you are looking for in the file. And then this morning, and also Jonathan, we've been talking about hosting services where you can store data. And there are multiple types of hosting services here. I'm mentioning cloud services or backup systems. These are all ways to version data. If you have a regular backup of your data, you can see it as a versioning system. You can travel back in time to see other versions of the file and what they looked like 1 month or 1 year ago. Of course, it's not a full dedicated versioning system, but it can be something that you can revert to if you don't want to make the effort to learn the actual software. Also, data repositories as Dataverse and Zenodo, they allow you to mark a version of the data. As I said this morning, Dataverse, once a version, a dataset is published, you cannot modify it, but you can modify another version of it and you label it as version 2. If you are using data lakes or any of these services, which are meant to share data between users, most of the time data scientists, they all have a way to version the data. And finally, if you're using workflow management systems like those, they also have as a side bonus the opportunity of storing and versioning the data. So if you have access to any of these systems, these are perfectly good way to version data over time. They are designed to do that, but of course, if you don't have access to it, you will need to go back to a file-based version control system, which will be the topic of the next slide. Do you have any question about the general topic and the list of tools here? Okay, so now we will focus on version control in the same sense of code control, but for arbitrary data types. Again, just a reminder, Git is the most used code versioning tool. It was designed from the beginning to be a distributed control version system, so there's no need for a main server. It can interact with GitHub, GitLab, and so on. And it's mainly an online tool, so you know Git init, Git commit, Git add, Git push, Git merge. There are all supplements of Git which help you work the workflow of creating a repository, committing, that is freezing the version of a file, pushing it to share code, merging, handle conflicts between coworkers. So you could theoretically use Git with text files, so CSV, PSV, YAML, JSON, XML. Whatever data file that is a text file, you could use Git to version it. The thing is that Git was meant for small files. So if these files are very large, you can end up in trouble, because if you use a Git pull operation, for instance, to get the last version of a file, it could try to copy multiple gigabytes of data on your disk if you're doing that on your laptop, and you might run out of space on the laptop. Because Git will always assume that the files are so small that copying a file from a board should not be something to worry about. Also, Git computes commit hashes at some points, and when it does that on a very large file, it can actually take resources and take time. The thing that Git tools like merge or diff, which try to find the differences between two versions of the code, they are all line oriented, meaning that they will focus line by line and compare lines by line, trying to realign lines if necessary. But actually, if there are line breaks in the data, Git will be totally lost as to how to interpret the data. So if you have a CSV file and there's a comment column with some carriage return in there, it can be completely lost. And also, if you run a column operation in the CSV file process, you exchange the place of two columns. Git will consider all lines to be replaced by a whole set of new lines, which is efficient because what you did is just swap the order of columns in the file, and there's no need to consider that this total file change. And also, all of these will fail with binary files. So if you still want to use Git in that context, something that you can do is a simple workaround, is to use a dump version of the data. We were talking about HDF5. There is a tool that's called H5dump that can create text version of the file. And since you went from binary to text, you can use a text version of what you said. So here are examples with MySQL dump. If your data is in the MySQL or SQLite system, you can dump the data and then commit those text versions simply with Git. It will not be very efficient, but it's the very least you can do with Git on binary data. Of course, it assumes that there exists a tool like this, produce a text version or a human readable version of the data from the binary version. Also, some of these allow recreating the binary version and some don't. So sometimes we'll have to store the binary data alongside with the text version. A slightly better approach is to co-version the binary files and the code that creates or alters the file. So here I'm assuming that I have some data which I infix with the version 1. And what I do is I put a reference either in the comments or as a git tag to version 1 in the create data script that generates that file. So the idea is I'm not able to create to version the binary file. What I can version is the code that creates or modifies the binary file. This is a perfectly viable approach, as long as you manually make sure to keep these in sync, and that can be a tedious task. So there have been attempts by the community to write extensions to Git that would help you do that. There are three often used extensions. One's called GitAnnex, the other is GitLFS, and the third one is GitFat, fat for fat files, because it was meant to hold large files. And you see, they have different technical ways of handling with the files. Some are based on symbolic links. So what GitAnnex does is it replaces in the repository the actual file with a symbolic link to the file that it stores in another repository, in another directory, which is not version control. GitAnnex has a separate set of commands to manage this file. So you will need to manually tell Git to handle the annex in a certain way or not. And it was designed for one file exchanges. When you're using GitAnnex, it is really meant to help you copy the data from one clone to another clone. It's not necessarily meant for working with the centralized storage. GitLFS is a bit the opposite. It requires a specific hosting service for the files. So GitHub offers that service up to a certain point, and then if your data is too large, you need to pay. It's based on placeholder files. So in your repository, the file is replaced by a small file that explains where is stored the actual file. And GitFat is also based on placeholder files and uses filters, so Git filters, so that file management is transparent. The same for GitLFS. By contrast with GitAnnex, that needs you to explicitly choose the files on which you apply the Git and the files on which you apply the annex tools. And then what I would like to show you is Datalad, which is a dedicated Git-like tool that works on GitAnnex. So it's one of the requirements is GitAnnex. And it tries to make the use of Git and Git annex a bit transparent for the user. So what I will show you here is based on the chapter 5 of the Datalad handbook. So this is the main reference for Datalad. Very nicely written. And so, as I said, it's built upon Git and Git annex. It's written in Python. The workflow is simplified compared to Git. If you know that Git has an index and you need to add and then commit, here there's no index, you can save it directly. I know some people are happy with that. You don't need to know Git to use Datalad, but if you know Git, then you can use a Git command in Datalad and you get the expected results. It was designed to be file type agnostic and application domain agnostic. You could store whatever type of data in whatever type of file format. It was meant to have a minimum set of custom procedures and data structures. So trying to keep the usage of data that simple. It can interact with many other systems. I said earlier that Git was meant to talk with GitLab or GitHub, and you will see that Datalad can talk with a whole set of other systems, among which you will find the one that we discussed this morning, like Datalad, Nextcloud, and so on. And also something that I really like about this tool is that the documentation is really well written. So the first step is how to install it. If you look at the documentation, they show you multiple ways to install it, depending on whether you have Windows, Mac, Linux, or whether you have root privileges or not. And so here, I just show you the part when they talk about a Linux machine where you do not have access, root access to, which typically is the case on the clusters. And so you see that with these 3 commands, you can install Datalad inside a Conda environment. This is not what we suggest. Of course, we don't like specifically Conda, but if you're playing with Lemaitre 3, on Lemaitre 3, you can load the Python module from the default release and Git annex, and then use pip to install Datalad. And if you do that, you will use the central install for Git annex and and also for Git that is compatible with Git annex, and you can use pip to install Datalad. In the future, we most probably will have Datalad installation globally available on all the clusters, but at this point in time, this is the preferred way to install it in the cluster. So when you have pip installed it, you can run Datalad and you get the small documentation here. Since Datalad is based on Git, it requires you to have Git at least minimally configured. That is, that Git knows your name and your email address, so that whenever you save, as we see a data set, which will correspond to a commit in Git, your name and your email address will be associated to that commit. So the first question is how to create a dataset, and actually what is a dataset? In Datalad, the dataset is a directory which is under version control, and you can either start from an empty directory with Datalad create, which will be the equivalent of a Git init, if you know Git, or you can start from an already populated data directory, and then you need to use a -f parameter to tell it that there's already something in the directory. So here, what you see is an example. I'm connected to Lemaitre 3, and I use Datalad create. I can give it a description, just to remember what is supposed to be in that data set, and I give it a directory name. So it will create a directory, and you will see that inside the directory, there's a .git subdirectory indicating that it has created the Git repository for you. But you'll see also a .datalad, which is where Datalad will store all the information it needs in order to help you manage this dataset. And then when you are in the dataset, you can use datalad status, which is the equivalent of git status. And it says that it has nothing to say working tree clean, which is very similar to git says when you ask for git status in the repository. Now is the time to add some file to the repository. So you do that by using any command you want to bring the file in the repository. And if you run datalad status, it says, okay, there's an untracked file in the directory. And what you need to do is run datalad save, and then a command, just like you would do when you git add and commit something, you give a command. And so here, datalad save add initial version of tar file. It gives you a small list of operations that he's doing, and then at the end, with datalad status, it says that the working tree is clean again. If you are a bit curious and you look into the directory, what you find is, besides the 3 subdirectories that were created when you initialize the directory, you see your file that actually has become a symbolic link to another file in the .git/annex subdirectory, which is where the git annex extension stores the actual files. And actually here is hidden behind those 3 dots is a hash of the version of the file. So if you modify the file, you will have multiple versions of the file here with different hashes corresponding to the commits that were done in Git. Okay, so you add a file, you save it, and then it becomes a symbolic link, and it actually escapes the repository. If you push the repository outside, the symbolic link is pushed, but not the file itself. If you want to modify the dataset, because it's treated the way it is, you first need to unlock it. So if you want to modify the tar file here, I first need to run datalad unlock. And what happens is that the symbolic link is replaced with the actual file, and now you are able to work on the file. So let's assume that I forgot to add the README file in the archive. I create the file and I appended it to the tar file. And datalad status says, okay, this file was modified, and I can save it again with a command saying that I updated the archive with a new file, here, a README file. And again, you see the result of the save and the status after the save, which says that everything is okay. Because datalad is based on Git, you can use git log to see the history inside the Git repository. So here, git log _ line shows after the new date, the initial commit when we use the datalad create. You see the first command and then the second command alongside the action, and that allows you to travel back in time to multiple versions of the file. Just like the clone and pull operations in Git, you have the same operations in datalad. So you can clone a repository or a dataset, and you can update to get new versions of the remote repository. So here, I will show you an example again on the method 3. If you remember a bit earlier, I created a repository or a dataset in my home directory, and here what I do is I will clone it in the global scratch. So I'm using cd to go to the global scratch, and I use their datalad clone, and then the path of the origin repository. If I then go into the repository, I see that my file is there. But actually, when I try to access the file, it says broken symbolic link. The thing here is that datalad, when it clones the repository, it will only clone the symbolic link and not the actual files. And it will be your duty to select the files that you want Datalad to copy back from the origin. And it makes sense if you are cloning a dataset on, for instance, on your laptop while it's stored on mass storage. You might not have 30 terabytes of storage on your laptop, and you still can clone the dataset, but you will need to choose a file that you want to copy back. Yes.
And the file that you choose to copy back, is it only the current version or all the history? Because I guess there is no magic at some point. In your example, there are several tar files stored somewhere.
Yes.
So if you choose to take that tar file back on your laptop, do you retrieve the different versions of it or only the?
I'm not sure, but I think yes, because you are able to switch to check out other versions. But I did not make the test. But that's a good question. If you use -export to Datalad status, it will tell you how many annexed files there are and how many out of the total volume available you have copied back here. And actually, that should be able to answer the question. Because so if you want to get a file, you need to use Datalad get and then the name of the file. And you see that there's no Datalad status -export tells you that there was one file and it is completely copied back. And actually, I think this is twice the actual size of the tar file. So I think it copied both versions. But I will check afterwards. And the opposite operation is drop. So if at some point you are working with a repository that is all the space on your laptop and you want to make room without deleting and losing any files, provided that it has been cloned from somewhere else, you can use a Datalad drop and then it will free the local space on the repository. So you can clone, but you can also, when you have cloned, you can register in a way. So I'm back here in the home directory. I can register the clone repository to the original repository. And so in my home directory, I use Datalad siblings add -d this means dataset. And so I wanted to add it to the current dataset. I can give it a name, so scratch, and then URL here, which is a file path, global scratch, and the name of the repository. So initially I had a repository in my home directory. I cloned it in a scratch. The scratch version has a reference to the origin because it was cloned from origin. And here I'm doing the opposite. I'm giving the origin a reference to the other repository in scratch. And so in Git terms, it's a remove. And so if you run git remove, you see that a remove has been added on the scratch, which allows you then to push and pull from scratch to home directory back and forth with a push and pull subcommits. You can also push the data to and create a directory, a repository otherwise. So the opposite of cloning is called create sibling. And here you see an example where I am in my home directory and I create a sibling on the CC storage by giving another path on the CC storage. And there is the opposite direction. So rather than going on the scratch and pulling data from the home directory, I am in the home directory and I'm pushing data to the scratch. Everything that I did about create siblings or clone, you can do also with remotely SSH reachable computers. So here I've shown you examples working on the same system on multiple file systems. But you can also create a sibling on mass storage while you are connected on the multiple systems. And actually, you can create siblings onto many different services. So if you have access to GitLab or Nextcloud or Dropbox or GitHub or Amazon S3 bucket, you can use Datalad to manage the upload of the data to those services. You just need to use a create sibling and then with the correct suffix based on the technology that is behind the hosting service that you are aiming at. You will need at that time to provide credentials and secrets and so on. But once it all is configured, you can push the data that you have been, for instance, generating on a cluster to any of those services by just using Datalad, versioning it, and then pushing it to the cloud service. Another nice feature of Datalad is that it allows you nesting datasets. So sometimes you will be using a dataset from some source and then modifying it, and you want to keep track of your own modifications, but you are not the owner of the origin. What you can do is nest your original dataset into your own dataset, and you can have multiple origins if you have multiple datasets that you want to merge into a single dataset that you will work on. Nesting datasets works with the clone command, where actually you use a clone command inside an already defined dataset. So if you have created an empty dataset, you can do so, and then you can use Datalad clone. Here again, you see I talked about -d. This is a long version here, dataset. Dot. And then here I give it the name of a data repository that is hosted on GitHub. So I have a test Datalad repository, and inside it I clone a Datalad set that comes from GitHub. And it does a few things, and actually what you see is that behind the scenes, Git has created a submodule. So if you are familiar with the submodule in Git, it's a way to incorporate repositories inside of the other repositories. And so when you have done that, if you go to the random directory, which is the one that was cloned from GitHub, you can use the git command and you see the history of this nested repository. And then if you go back to the parent, you need to save the dataset, just like you commit when you create a submodule. And this will actually freeze the version of the parent of the removed version of the file that you have imported in your own repository. So you have a file which is called random.date at some point. You have cloned it from GitHub, and you start working on it, and then you know at which point in time this file was when you first started working. Then, if you want afterwards to update the file, if the people who give you the file say, okay, we have been correcting some things inside the file, you need to update your version, you can use Datalad pull again on the file to get the version. And you will have to commit again in your own repository the fact that the removed version of the nested dataset has changed. Does this make sense to you? So same ideas with nested Git repositories, except that it's for data. Now I would like to show you a nice thing that Datalad offers. If you remember, I said earlier that one of the viable options to use Git on binary files was to actually co-version the binary file and the code that creates or modifies the file. And actually, Datalad allows you to do that all in one. The idea is that there's a run command that you can use on your dataset. And here is an example. You remember I downloaded a random.dat file from GitHub, someone that who shared that with me. And what I do here is Datalad run, and then I give it a commit message that says count number of zeros in the random file. And then here you see the actual command that will count the number of zeros in the file. When I start enter, when I hit enter here, you see that something happens. And at the end, I have the count.txt file, which is the one in which I redirected the output of the grep command. That holds actually the number of zeros present in the file. And if I run git log, you see that there's a special entry here, datalad run cmd, with the commit message I entered here. And so this actually did multiple things. It ran the command that I give it. It saved and commit the file that was created. And also it saved in the commit message the command that was run. So behind the scene, the command that you run has been recorded. And so you know that the version in the file from this commit was created with this command exactly. There's a rerun option. So if you look at the log here, and actually this version of the log, you see here the small version of the hash of the commit, and you can refer to this operation to run it again. Actually, if you give that version a name with the git tag, you can use this tag, so version 2, maybe version 3, which is more explicit than this reference. But you can run datalad rerun of the commit hash, and it will start again. If at that point the source file has changed, which was not the case here, it will do everything it needs to correct in the commit the version of the count.txt file. So you know that if you haven't pushed any change to an online repository, you can still amend the commits that you have done. And so Datalad knows that, and if it will try to modify the commits behind the scenes if you did not already publish it. But if you publish it, then it will publish it as a new commit, as a new version. And so what this means is that you can, with this, share the code that created or modified the data alongside with the files that were commit and saved in data. Any question about this? Very simple tool, like 5 or 6 subcommands. If you know Git, you will feel at home with Datalad. And you see the example here, just a way to modify and commit versions of a binary file alongside information about provenance and information about how the file was created or modified. If you want to read more about Datalad, this is the website where you will find information. There are tutorials on GitHub, and there's a 2-hour video here that explains what I just explained, but in longer and in more details. Any question about this super tool? Will you be using it? No, I never used it. If you use it, let me know. So, in summary and conclusions, data versioning is basically the same stakes and challenges as code versioning, except that we will at some point have to deal with large binary files, and there is no clear solution. You could use a file writing library with built-in versioning in it if you are using a DL5. We know that there's a library that can do the management of the versions for you. If you have access to a hosting service that has features versioning, feel free to use it. Of course, it's very nice not to do the work by yourself. But if you need to work with files and you want to version the files the same way that you version your code, you can use either of those workarounds, which is either version a text dump of the data or version code that alters the data. You can rely on Git extensions, and I was talking about Git fat, Git LFS, and Git annex. And actually, based on Git and Git annex, Datalad is a nice little tool to work with data files in the same way you would work with code for sharing, publishing, and tracking versions of your data. If you want to read more, you can click on those further references. These are specific to data versioning tools and data version control. These are a way to choose how you label your versions. So Calver is calendar versioning. So you label a version of the data with the timestamp at which it was created. Semver is semantic versioning, which is the one when you see a version number with a three numbers separated by dots. We talk about major, minor, and patch. It's a way to decide on the numbers that you put there in order to convey a meaning. And then here are some tips to write commit messages. It's always nice to make sure that the commit messages does not say commit or message or next one, if you remember the first image in the slides. And so these offer guidance and guidelines on how to write structured commit messages that allow you to find earlier versions of the dataset easy.